Here's from your textbook, page 323. So you're curious about which one, sodium plus?
Yeah.
And neon, we're not going to ask you about noble gases. So did you have an alternate one besides neon? Yeah, we're not going to ask you that. Yeah. Okay, cool. Sweet. Next. Yes, in green right there.
When you're doing polarity of I5 minus,
Yeah.
how is it polar if all of the atoms are the same?
Okay, she's wondering how can it be polar if all the atoms are the same? And we did a specific example of I5 minus. Let me just draw it in its actual formation. It's polar because these iodines are not counterbalanced necessarily by these electrons here. So the electrons can actually also cause a slight dipole. And so, because these will be in lobes over here, like that, and that'll cause, again, an unequal distribution of electrons. Now, it would be different if it were just, there was no electrons involved, it was just the pure atoms, then what you're saying might be true. But that ends up never being the case. Good, good question. Next. Yes, I saw hers first. Yes. Practice final. Okay, so tell us the year. Fall 2009? Oh, winter 2009. Yeah, what number? Winter 2009, number 18. This is with the electron? This one right here? Okay. So in this case, the electron's moving this fast. You have a velocity and you want the wavelength. The only possible equation with velocity and wavelength has to be that Broglie equation I wrote a little earlier, which is this one. Okay, so H is a constant, given on the back of the exam. M is the mass of an electron, given on the back of the exam. I think it's to the minus 31st, but you can look. And then the velocity is given in the question. Is that okay? Okay. And then you'd have to convert, this would be in meters. And then 1 meter, and I think this is also on the back of the exam, is 10 to the 10 angstroms. Okay? Good, good. Okay, there's somebody else here? No? Yes? What year again? Same exam, winter 2009, but now going over to number 7. Is it about the 5 dxy orbital? That one? Okay, and you want to find out what's false about this. Well, I guess I should show everybody. Yeah, there we go. Okay. The 5 dxy, I guess I need to draw it. Now that I think about it. The 5 dxy would be on the xy plane, that's the xy. And when there's no squares, it's in between the axis. So something like that. Okay. So the z-axis is going like this, up and down, towards you, basically, from the screen. So the first one was, okay, this is not totally going to work here. There we go. Okay, the first one was, there's a nodal plane in the xz. Yeah, this is a plane. How about the yz? Yeah, that's a plane. It will go that way. How about for an electron in the 5dx orbital, there's a higher probability of finding an electron farther from the nucleus than if it is the 5s orbital. That's true too. Does anybody know why? You're getting there. It could be sort of related to the nodes, but we could be more specific because of shielding. So and the nodes are involved in that shielding, they make it bigger. And so because the 5s is the least shielded, it will be closest to the nucleus. P is more, D is more, F is the most shielded, and so those are further from the nucleus. Okay? And then it can hold up 10 electrons. Is that true? How many electrons can this hold? 2. Yeah, so that's the wrong one. The 5d orbitals as a set, all 5 of them can hold 10, but each one, so the wrong one is D. Cool, who's next? Good. Yes? Bond order is not related to sigma and pi bonds. Do you want to tell me the question? Fall 2009, number 23. That's this mess right here. Okay, which one in particular? How do you find sigma and pi? Yeah. No, it's not related to MO diagrams. You just want to draw the Lewis structure. So let me do that. So she's wondering how to find sigma and pi for this monster table, which is a pretty typical table to see on a final. Do you want me to draw it like with you, or just tell you what the Lewis structure looks like? Okay, the Lewis structure should be something like this. For the first one, and for the second one, is H2SO4. Something like that. Is that kind of what you got? Okay, so for sigma and pi bonds, you want to know for a single bond, there's a sigma. For a double bond, you count 1 sigma and 1 pi. And for a triple bond, you count a sigma and 2 pi. So every bond has a sigma. So first, let's count all the bonds of the first one. 1, 2. So I would say there's 2 sigmas, because there's 2 bonds. Every bond has a sigma. For the pi's, this is contributing 2 pi's. This is 2 pi's. Is that okay? For the next one, let's do the pi's first. There's 1, 2, because each double bond contributes 1. So you should get 2 pi bonds for the second one. For the sigmas, count every bond. 1, 2, 3, 4, 5, 6. Is that okay? Yeah, so from the Lewis structure. Remember this? Here, this is your key. Okay, cool. Who's next? Yes, I saw your hand earlier. Fall 2008, number 20, fall 2008, number 24. Oh gosh, you picked a hard one. Of course, you all picked hard ones. This is Topadakis likes these kind of questions. You're in his class. This is his question. There's a gas mixture of CH4 and C2H4, okay? And it's 5 grams, so total this is 5 grams, okay? That's burned in excess of oxygen. So what I'm going to do, each one undergoes combustion, okay? So I'm going to write the reactions separately, though in this container they're happening all together, okay? But both of these reactions are happening simultaneously. Is that okay? So now here, the CO, it says in the question, total CO is 14.5 grams. Okay, that's it. What's the mass percent of the sample was ethylene? So we want to know the mass percent of ethylene, which is C2H4. Hint, write the chemical equations. Duh, I did that. Sweet. Okay, before you start working on the problem. All right. There's a couple ways you could possibly do this. It kind of what your fancy is. This is, I'll just show you a way, okay? It may or may not match with what they have in the answer key. So let's say there's X grams of this and Y grams of that. Okay, just to pick some variables. So X plus Y equals 5. Is that okay? So then, but also, let's balance this by the way. 1, 1, 4, 2 here, 1, 2, 4, 2 there. And then 2, 2, 4, 2, and then 1, 2, 4, 3. Okay? So now you could say, well, X is in grams times the molar mass, to change to moles from the periodic table. Now it's moles of methane. I'm doing it for the top one. And then there's, let's go to CO2, 1 mole of CO2 for every 1 mole of CH4. And then 44 grams per mole will get me the mass of CO2. Is that okay so far? I just did stoichiometry. The only thing is I don't know my initial number, which is fine. Okay, and then you can also do the following. So this will be a number times x, basically. Some number times x. And then you can do this again for y. For C2H4, that's something like, is it 26 or something like 28 grams per mole, right? Yeah. Okay, and then there's 2 moles of CO2 for every 1 mole of C2H4, and then 44 grams per mole equals the mass of CO2 for the second one. Okay? Now I'm going to get a different color. Oh, this plus this equals what? 14.5. 2 equations, 2 unknowns. This is the mass of carbon dioxide here in this reaction, and this is the mass of carbon dioxide in this reaction. So we're adding them up to get 14.5. Now I have 2 equations, 2 unknowns. I'll let you solve it. Is that okay? Okay, cool. Who's next? Good question. Yes? Okay. I can't quite see it back here. Whoa, hold up. Okay. What exam? Fall 2009. What number? 28? 28 B and C. Oh my God. D. 28D. Oh my gosh. You picked this one? Okay. She's talking about this. Look at this monster. Can go crazy. Okay. A valve connects 2 gas tanks. Let me draw this out. There's 2 gas tanks connected, and the first tank is 1.23 liters, contains oxygen gas at 724 millimeters of mercury. The second tank is 2.05 liters, and it's 698 torr. And the second tank is nitrogen, the first one's oxygen. Okay, they open the valve. When the valve is open, the following reaction occurs. N2 plus O2 forms N2O. Okay? Okay, and the temperature is 25 degrees C. Okay, so the ones you're skipping is what's the limiting reactant, which has nothing to do with gases, it's just a normal limiting reactant one. The second one you're skipping, the moles of the excess reagent, so that's still limiting reactant, so A and B are limiting reactant. C, now is where we get into gas laws. I forgot, you said not C, just D. Okay, so C, just for my own joy here. C, let's see, what is the pressure of the N2O form? And so based on moles from the previous question, use the ideal gas law. Okay, now, what's the total pressure in the tanks for the last one? Total pressure in the tanks for the following reaction. So what they had to do for the last part, this is part D, Then we want the total pressure, I think, left over when the reaction is totally finished. Let's see, let me make sure I'm getting that right. Yeah, so to find what you need is the partial pressure of oxygen. So what happens when this reaction occurs, O2 is in excess, okay? So what's left over when everything happens, the valve's open, N2 and O2 react, form this, and there's leftover O2. So to get P total, it's the partial pressure of N2O plus the partial pressure of O2. That's all that's left over because all the nitrogen reacts away. Okay, so there's no nitrogen. If there was nitrogen left, you've got plus nitrogen. So the pressure of NO2, this one right here, is part C. Number C, whatever. Part C. The previous part, we just found that. Is that okay? So all we need to find is the partial pressure of O2, which is what we need to calculate this. So the partial pressure of O2. You can always punt to the ideal gas law equation. And then everything is pretty much given. You have the moles of O2 from before. From before you have the moles of O2, you have the constant from before, you have the temperature, and you have the volume, which is the sum of the two things. Is that okay? Okay. So again, one more time, it's a little bit difficult skipping the first three parts. But in general, what happens? A reaction occurs, you have this, you have O2 in excess that you found in parts A and B. In part C, you find this one, and basically add these to get the total pressure. Okay, who's next? Yes?
And you would need to balance the equation.
Yeah, you totally need to balance the equation, you'd be dead. This is, I guess if you did... Does that do it? Yeah, okay. Yes? Fall 2009. Okay, I'm ready. 26. Oh yes, also painful one. No wonder you're asking. Okay. Also okay. How does this work? You're mixing X milliliters of wine, which is, so you need, your grammar skills would be on point for this question. X milliliters of, which is 0.0030 molar in sugar. Okay? You got that. Okay, with plus 20 milliliters of wine. Okay, so number 26, fall 9, which is 0.0010. Crazy good question here. Let's see, which is, okay, the resulting wine. So that was the first sentence that said that. The resulting wine, new color. This. Okay, the resulting wine is mixed with 30 milliliters of wine, which is 0.0020 molar. Okay. The resulting wine, new color, is, okay, now we're at the end. This thing is 0.0015 molar in sugar. What's X? Okay. So do you want me to solve it too, or was just the logic of what the word said? Okay. So that's it. This is some volume here. You basically want to solve for X. Yeah. The total volume at this point would be 50 plus 20 plus X, which would be, no wait, 30 plus 20 plus X, which would be 50 plus X. So you have the final, you have the initial, it's kind of like a dilution formula. Okay, yes?
Can you draw the MO diagram for O2
O2, 2 minus. MO diagram. You just want the middle, or do you want the edges? The atomic orbital. Everything?
Yeah.
Okay. So this is good. Whose class are you in? Nice. That is the correct answer. Okay. So I would just say two minuses come together to make an 2 minus. Again, this is the thing I was talking about before, that different classes might have a slightly different opinion on the edges. Okay. But you're my class, so good. Okay. So draw this. Now for oxygen, it would look like that. 1, 2, 2, 1 for the orbitals. Okay, sigma to S, sigma to S star, sigma to P, pi to P, pi to P star, sigma to P star. Is everything okay so far? I'm just drawing the template for anything with oxygen or above in atomic number. This electron configuration would be 1s2, 2s2, 2p, 1, 2, 5. Same for both sides. So now let's fill it in. 1s2, 2p5. 1, 2, 3, 4, 5. 2s2. 1, 2, 3, 4, 5. Are we okay so far? So I just filled in the electrons, both row minus on each side. I have the standard template. Okay? 1, 2, 3, 4, because there's 2 on each side for a total of 4 in the middle. The top one has 5 on each side for a total of 10 in the middle. 1, 2. If anybody doesn't know how to fill these in, you can watch my pen. 3, don't pair yet, 4. And then 5, pairing, 6 pairing. Now we go up. 7 unpaired, 8 also unpaired, 9 pairs, and then 10 pairs. We got it. That would be the MO diagram. Did you want the bond order magnetism, or are you good with this? Okay, cool. Yeah. All right, who's next? Yes?
On the exam, will you give us the outline for the MO diagram, or do you want us to draw the actual outline?
She's asking, will the final give you the design or template, or do you have to draw it? I can't answer that question. Yes. Either. Fall 10, fall 2008. Number what? Fall 2008, number what? 8? The one with the dipole moment? Yeah, this for some reason, I have this in another video. This is like my most hit video, and it's so random. But smallest dipole moment. Anybody know what's the smallest possible numerical value they could have for a dipole moment? It's 0. So you're wondering which one has a 0 dipole moment, or in other words, which one has no dipole, or which one is non-polar. Okay, now to correctly do this, I have to draw all of them. But you can kind of look at it. I'm immediately going to cancel out A, because with a chlorine on the right, there's no way this could be non-polar. Is that okay? Yeah, I almost don't even have to draw it. CO, immediately you can cancel out, because there's a C on one side and oxygen on the other. There's no way that could be non-polar. So it's between C, D, and E. Okay, let's do E. Oh, do you want me to just tell you what the Lewis structure looks like? Or do you want me to draw it with you? Just tell you. Okay. Make sure, everybody else, you can do this then. So I don't even need to write this. Here's water. It's not that one for sure. Because that one's asymmetric, can't be that one. The CF3, here's that one. Remember, you have to do shape. In order to correctly answer the polarity question, shape technically must be done. This one's the non-polar one. You can see it's fully symmetric on both sides. Okay, and the other one though, just for completeness, let me see if I can trick you. Is sulfuric acid. Is this symmetric or not symmetric? So I'm asking, is it polar or non-polar? It's hard to answer without drawing the 3D structure. So technically, you'd want to draw the tetrahedral shape of the sulfur. Remember, the oxygens have 4 groups and 2 lone pairs, so they're bent. And now when you draw the tetrahedral shape, you should see definitely it's asymmetric. This one's polar. This one's non-polar, so it's definitely D. Is that okay? Okay, who's next? Yes, in red up there. How do you find if a bond is, if a molecule is polar? If the bond is polar? Oh, which one's the most polar? We'll give you on the back of the test an electronegativity table that exactly, literally, looks like this. This is it, in fact. And these little numbers, you just subtract them and take the absolute value of whichever one has the biggest difference, is the most polar. Is that okay? Yes? If it's a double bond or a triple bond, does that affect polarity? No. No, not for the question that I think he's asking. Okay, last question. Yes, you win. Fall 2009, 23. Fall 2009. This will be the last one I do, then we'll break. Fall 2009, number 23. I'm a little scared if it's an extremely difficult problem. Oh my gosh, you're asking me this? Which one in particular? Winter. Good. Okay, sorry, my hearing is bad. Oh gosh, it's even worse. This one? Okay. Okay. The first sentence is totally irrelevant. The second sentence, hydrogen peroxide is delivered 50% by mass solution. And it's hydrogen peroxide, H2O2. But they need to dilute that to 3%. They need 20 gallons. How many gallons does, how many gallons are needed? Oh, this is a dilution question. So this is the molarity. Is that okay? Okay. There's only one problem. We're cool not converting gallons to any other unit. That's fine. Gallons are gallons, so you can keep those units as is. I do need to do a conversion up here with the molarities in this case. They're not molarities, they're percent by mass. And the reason is they have different densities. So what I'm going to have to do is convert this to molarity with the given information, and then convert this to molarity, and then plug into this equation. Do you want to see me do one of those conversions? Yeah. Oh, well, you didn't have to answer. Everybody else is excited to learn more. This is a pretty typical conversion, so make sure you're comfortable with this. Let's do the 50%. Okay? The 3% would be the same. Here's what you need to know. It's 50%. It'll always give you a density. So it's 1.197 grams per mil. And that's usually about all you need. So let's try it. 50%, that means 50 grams of the H2O2 per 100 grams of solution. Okay, that's what 50% means. All right, so what I want to do is change the top to moles and the bottom to liters, because that's molarity. So let's work on the bottom first. I'm going to use the density, 1.197 grams per milliliter. So now, when you're given a density, it's going to be a solution density. So I'm canceling the grams of solution for milliliters now of solution. And I don't want milliliters, I want liters. So a simple SI unit conversion gets me to liters. Now for the last part, how do I do the top? Because I need this to be moles. I'm really happy with this liters right here. That's good. That's my denominator of molarity. For the top half, I need the molar mass. Let me see if it's written anywhere here. Yeah. 34.01 grams per mole. Now notice the grams of this is of H2O2, cancel. So now I'm very happy because I have moles on the top. This is going to be the mole, this will be M1. What you'd want to do is repeat that exactly for the 3% solution. The only difference is this is a different density, and that's given in the question. Is that okay? Okay, and then just plug and chug. All right, I think that's a good place to stop. Good luck on your final.